Hello, this is Dr. Armand bringing you another exciting video lecture in General Chemistry 2 topics. Today we'll be talking about solutions and colligative properties. So sit back and relax and enjoy the show. So like I just mentioned, we'll be talking about solutions and colligative properties. And so this is a little bit different than the previous set of topics, which deal with the solid, liquid, and gas states. And so to kind of refresh or review over topics we've already covered involving intermolecular forces, I have a few review problems to look at. So one of the things we learned about when talking about solids, liquids, and gases is the different types of solids. So in this question, we want to know which of the following is a molecular solid. So there could be more than one answer. So molecular solid is a solid made up of two or more atoms that are nonmetals. Because these are made up of molecules. So we're looking for the choices in which there are two or more atoms, and these are only nonmetals, not metallic, not cation, anion, not covalent network, not atomic. So the formula has to have two or more atoms, which are all nonmetals. It can be the same nonmetal or different nonmetals, but it has to have more than one nonmetal. So we look at the first one, we look at sodium. There's only one of the sodium, so it can't be a molecular solid. And since it's a metal, it's actually a metallic solid. So we can scratch off that one. We look at the next one, ammonium fluoride. Well, here it all has nonmetals. However, these are not atoms. These are ions. So we have the ammonium ion, which is positive charge, and we have the fluoride ion, which is negative charge. So this cannot be a molecular solid. It's an ionic solid. Next, we go to P4. Now, phosphorus is a nonmetal, and it has two or more atoms that are nonmetals. So this is a molecular solid. We go to D. D is neon. Neon, there's only one atom. It's a nonmetal, and it's from group 18, so this is an atomic solid. C, graphite, is a covalent network solid. It's one of the few examples of covalent network solids. Calcium hydride, we have a metal and a nonmetal. This is an ionic solid. And then SO2, we have nonmetals, and we have more than one nonmetal. And these are two different nonmetals, by the way. So this is a molecular solid. So C and H are molecular solids. Another thing we talked about were for crystalline solids, we discussed about unit cells, which is the smallest repeat unit that gets repeated in the entire crystal. So the unit cell has all the atoms that are symmetry equivalent, and then this box that has all the atoms or molecules or ions gets repeated in 3 dimensions. So here we have this unit cell. We want to know how many atoms are in it. So we have to refresh from what we know about unit cells. So when an atom is on a corner, it's only 1/8 of an atom. Because remember that there are 7 other unit cells that touch that atom. So an atom on a corner is 1/8. Atom on a face So if an atom is on a face, it's going to touch one other unit cell, so it's 1/2 of an atom. And an atom on an edge being this part, this is the edge we're referring to. So these are edges. So atom on an edge equals, since one edge touches 3 other, it's going to be 1/4 of an atom. So knowing this, we can determine how many atoms there are in a unit cell. So this cube, or this unit cell, has 8 corners. Each corner has an atom. So we have 8 times 1/8 equals 1 atom. And this cube has 6 faces. Each face is 1/2 of an atom. So that's 3 atoms. So this is a total of 4 atoms. Or this could also be ions. So for example, if this was ions, it could be aluminum chloride, for example. Aluminum having 1 cation, chloride 3 anions. So it could be that. But this has a total of 4 entities in the unit cell, which could be atoms or ions, or maybe even molecules as well. Another thing we discussed was different types of intermolecular interactions. So here we know which of the following would observe dipole-induced dipole interactions. Select all that apply. So what do we have here? We want to look for dipole-induced dipole interaction. So dipole interaction is the main interaction in polar compounds. Induced dipole interaction is the main interaction in nonpolar entities. So what we're looking for is a polar and a nonpolar entity in the combination. So if we see a polar and nonpolar entity in the combinations given below, that's going to give us dipole-induced dipole. So in A, we have this carboxylic acid. It's polar because it has this carbonyl oxygen and this hydroxyl group, which makes it polar. Also, it has hydrogen bonding. This amine is polar as well because it has that NH2 group. So this would not be dipole-induced dipole. Next, we go to B. We have chlorine Cl2, which is nonpolar, and chlorocyclohexane, which is polar, because here there's a dipole moment. It doesn't get canceled. So this is a polar molecule. And so B would have a dipole-induced dipole. Next, we go to C. We have trimethylbenzene. And you see it's only just containing lines. So whenever you see something that only just contains lines, it only has carbon and hydrogen. So since it only has carbon and hydrogen, this is going to be nonpolar. Now if we look at this propanol, this OH group here, this is polar. So we have a polar and a nonpolar. This would have dipole-induced dipole interactions. Next, we have benzene and krypton. Benzene, as you see here, only contains lines or sticks, so it's nonpolar. Krypton is also nonpolar. So this would not have dipole-induced dipole interactions. Lastly, we go to E, where we have butanol, which is polar, because of the OH group, and potassium ion, which is an ion. So this would not be dipole-induced dipole. So the correct answers are B and C. Those would observe dipole-induced dipole intermolecular interactions. And then lastly, we want to look at one more example involving intermolecular forces. We want to know which of the following would have a high vapor pressure. So again, when we have a high vapor pressure, this is going to equal low boiling point, which equals weak intermolecular forces. So again, high vapor pressure means it vaporizes very easily, which means it has a low boiling point and weak intermolecular forces. Likewise, if we have a low vapor pressure, equals high boiling point equals strong intermolecular forces. Again, it's all relative what we define as weak and strong. But something, for example, ether, which has a very low boiling point, has a very high vapor pressure, that's weak intermolecular forces, whereas something like water, which has a low vapor pressure, very high boiling point, it would have strong intermolecular forces. So which of the following would have the highest vapor pressure? So again, here the key is the highest vapor pressure, which means it's going to have the weakest intermolecular forces. So we got to distinguish between the ones that are polar and non-polar. So the first molecule has two OH groups. This would be polar. Next we have C6H14. Again, it only contains sticks or lines, whatever you want to call it. So this is non-polar. Xenon is an atomic solid. It's non-polar as well. C8H18, again, you notice it only has sticks. This is non-polar. Next we have THF. Well, THF has this oxygen here, which makes it polar. And then we have orthodifluorobenzene. Again, the fluorines are on the same side, so this is going to have a dipole moment. So this is polar as well. So now looking at the non-polar, again, the molecular weights are what we use to determine which one is the stronger or weakest intermolecular forces. So we have C8H18, C6H14, and xenon. So here if we look, the molecular weight for C8H18 I believe is 114. Now C6H14 86 grams per mole, and this is 131 grams per mole. Now, we have to decide on C8H18, C6H14, or xenon, and we have the molar masses. Based on the molar mass, you would say C6H14. But one thing you got to keep in mind is that C8H18 and C6H14 are molecular solids, whereas xenon is an atomic solid. Since xenon is an atomic solid, it would actually have weaker intermolecular forces than C6H14 or C8H18. Because again, it's an atomic solid. Atomic solids are weaker intermolecular forces than a molecular solid. So the correct answer would be C. C would have the highest vapor pressure at a given temperature, of course. So now getting into solutions and colligative properties, when we talk about solutions, we're referring to the solute and the solvent. Remember, solutions are a homogeneous mixture, and so the solute gets dissolved into the solvent. So it's usually the one in the lesser amount. So the lesser amount is your solvent, the lesser amount is your solute. The greater amount is your solvent. So for example, when you dissolve sugar in water, sugar is the solute, water is the solvent. So again, water is in greater abundance, it's the solvent. Sugar, which is in less abundance and was dissolved into the solvent, is the solute. Now, sometimes to describe if something is soluble in a solvent, we say for miscible, usually referred to as liquid. So if your solute is a liquid and your solvent is a liquid, we say the solute is miscible in the solvent. So for example, ethanol is miscible in water. Or hexane is immiscible in water. Solubility tells us what's the maximum amount of solute that will dissolve in a fixed quantity of solvent at a given temperature. So solubility is related to or affected by the temperature and the amount of solvent. So again, the solubility tells you how much of that solute can be dissolved in a fixed given quantity of solvent at some particular temperature. And the key principle is like dissolves like. And this is in reference to intermolecular interactions. So what does this mean? It means nonpolar likes nonpolar, polar likes polar, and polar likes ionic. So ionic has similar intermolecular interactions as polar compounds. So if something is nonpolar, it's going to dissolve in a nonpolar solute, such as oil and hexane. If something is polar, it's going to dissolve in a polar solvent, such as well, sugar dissolves in water. Methanol is miscible in water. Sodium chloride dissolves in water. So those are all examples of polar solvents dissolving polar and ionic solutes. So, and now we need to talk about the intermolecular forces in solutions. Similar to what we talked about with intermolecular forces of solids, liquids, and gases. So first off, when you dissolve a salt in a polar solvent, say water molecules, the ions compete with the hydrogen bonding that's occurring in the water molecules. So you get what's called a ion dipole interaction. So you dissolve a salt in water, the ions compete between interacting with the water and the water interacting between themselves. And so then you get this ion dipole interaction that occurs. And as discussed in earlier lectures, ion dipoles a pretty strong interaction, therefore causing you to take more energy to get to the boiling point of water, for example. And the water molecules, the way they arrange around the ions is in hydration shells. Usually the cation coordinates to the oxygen, which is the negative in the water, and the anions coordinate with the hydrogen part, which is the positive in the water. So the bigger the ion, the more waters that can fit around the metal. So for example, lithium plus can have about 4 water molecules tetrahedrally coordinating with the lithium, whereas sodium and fluoride can have 6. So the bigger the cation, the more water molecules can coordinate around it. Now, that's when you have a salt and water. If you have 2 compounds that have hydrogen bonding, then you can have a hydrogen bonding interaction. So for example, you dissolve methanol in water, methanol is miscible in water because they have similar intermolecular forces as water. So you get this hydrogen bonding between the methanol and water. You can also have dipole-dipole interactions between solute and solvent. So if our solute is ethanol, which is an aldehyde, so you have this negative charge here, positive charge here. It's going to interact with chloroform, which is also a polar compound, has a positive charge here, negative charge here. So you get this dipole-dipole interaction. But it takes two polar compounds to produce a dipole-dipole interaction. Next, we have ion-induced dipole. So here for an ion, we have to have a salt, and it's going to dissolve in hexane. So the anion, since it's negative, will interact with the positive side of the temporary dipole in your nonpolar compound. The cation, let's say it's sodium, would interact with the temporary negative side of the temporary dipole. So you get this ion-dipole, ion-induced dipole interaction. This is very weak, again, because salt doesn't like to dissolve in nonpolar solvents. So it's a very weak interaction. Next, we have dipole-induced dipole. So dipole means it's polar. So for example, we take water, we mix it with xenon. Xenon is nonpolar, it has a temporary dipole. So the negative end of water interacts with the temporary positive end of xenon, and you get this dipole-induced dipole interaction. So again, dipole-induced dipole, you got to have a polar compound and a nonpolar compound, like a polar solvent and a nonpolar solute. Now with dispersion forces, you just have to have two nonpolar compounds. So for example, octane and hexane, they're both nonpolar. They're going to be miscible in one another. So these are the different types of intermolecular forces that occur in solution. Now with liquid solutions, we know that salts are soluble in water. And this is due to the ion-dipole force that we discussed, and this is because it has similar strength. So the strength of the ion-dipole force is in similar strength to compare to the forces between the ions and the hydrogen bonds. So since the ion-dipole force is in similar strength as compared to the forces that are holding the ions together or the hydrogen bonds together, we get this ion-dipole interaction. So that's why the most salts are soluble in water, because the solute-solvent interaction is in similar strength or even stronger than the individual solute-solute and solvent-solvent interactions. That's why salt is soluble in water. Now, salt is not soluble in hexane because the solute-solvent interaction, which is the ion-induced dipole, is weak compared to the attractive forces in the solute, the ions. So since the solute interactions are stronger than the solute-solvent interactions, this is why salts are not soluble in hexane. Whereas for salts in water, the ion-dipole force, which is the solute-solvent interaction, is similar in strength to the solute-solute and solvent-solvent interactions. Now, oil is not soluble in water because the solute-solvent interaction is dipole-induced dipole, and this is weaker than the solvent-solvent interactions, which is hydrogen bonding in water, and the solute-solute actions, which is the dispersion forces in oil. So since those are the collective interaction is weaker than the individual interactions, oil is not soluble in water. Same reason why salts are not soluble in hexane, because the collective interaction is weaker than the individual interactions. Oil is soluble in hexane because the dispersion forces in one can replace the dispersion forces in another. So again, the solute-solute, solvent-solvent interactions, which are both dispersions, can be replaced by another dispersion forces. This is why salts are soluble in water and not hexane, and oil is soluble in hexane and not water. Water is polar, hexane is non-polar. Now with alcohols, alcohols have a polar and non-polar component. So the CH chain is the non-polar component, and the OH is the polar component. So for example, here I drew pentanol. So again, the carbon chain is the non-polar component. The OH group is the polar component. Now, as the non-polar component gets bigger, the dispersion forces between the non-polar component get stronger than the forces between the hydrogen bond. So with alcohols that are 1 to 3 carbon chains, when you put them in water, the hydrogen bonding between the solute and the solvent, so the interactions between the methanol itself and the water itself are replaced by the methanol water interaction. So the solute solvent interaction is stronger than the solute and solvent interaction. So your 1 to 3 carbon chains alcohols are soluble in water. And we'll see a chart in the next slide that shows you how it tapers off as the chains get longer. So now when we're talking about larger alcohols, those chains that have more than 5 carbon atoms, these are not soluble in water. And this is because that very long non-polar chain, the dispersion forces become stronger and it breaks up the hydrogen bond. So since non-polar forces are becoming more predominant, making the hydrogen bonding less effective, so large alcohols starting with about 5 carbon chain are not soluble in water. Now when we flip to hexane, and the reason we use water and hexane is because water is a very common polar solvent, hexane is a very common non-polar solvent. So hexane has very low solubility for the smallest alcohol, which is methanol. And this is because the hydrogen bonding forces in methanol are a lot stronger than the ion-induced between the weak dispersion forces and the hydrogen bonding. The individual forces cannot overcome the strong hydrogen bonding within the alcohol. So methanol is not very soluble in hexane because again the solute-solute interactions are stronger than the solute-solvent interactions. So methanol does not dissolve in hexane because hydrogen bonding is very effective, is very strong in methanol. Now, when you go beyond 1 carbon chain alcohols such as ethanol, propanol, butanol, etc., then dispersion forces between the solute and solvent can replace the dispersion forces within hexane. So then when you go to 2 carbon, 3 carbon, 4 carbon chain alcohols, dispersion forces get strong enough to replace the dispersion forces between hexane itself, so you get this solute-solvent interaction that occurs. So again, very small alcohol chains, usually 1 to 3, are soluble in water because the solute-solvent interaction is stronger than the individual interactions in the solute and solvent. With larger alcohols, starting with carbon 5 chain and bigger, these are not readily soluble in water because there's a longer non-polar component, which means the dispersion forces are greater and it breaks up the hydrogen bond. Whereas in hexane, Hexane is solubility is very low with methanol because methanol has a very strong hydrogen bonding, and the hydrogen bonding between the alcohol doesn't get replaced by the induced ion, the dispersion forces and the hydrogen bonding. Dispersion forces and dipole cannot overcome the strong hydrogen bonding within the molecule. So this should be induced dipole. So the dispersion or induced dispersion and the weak induced dipole forces can't overcome the hydrogen bonding that is occurring with the alcohol. So that's why methanol is not soluble in hexane. Whereas your carbon chains that are greater than 1, there's sufficient dispersion forces that it can break the dispersion or interfere with the dispersion forces between hexane and dissolve or become miscible in solution. Here's just a chart. So as you see with solubility in water, we see that methanol, ethanol, propanol are very readily soluble in water because, again, the hydrogen bonding component is strong enough that it can penetrate the hydrogen bonding between the water to get this solute-solvent interaction. But you see, when we go from 3 carbon chains to butanol, we see it goes from infinity to 1.1. So infinity means it's readily soluble. 1.1 means it's only 1.1 moles per 1 kilogram of solid. It's a very dramatic drop in solubility. So after you get the 3 carbon chain alcohols, after that, alcohol solubility in water is very poor, and this is because the dispersion forces are becoming more predominant and breaking up the hydrogen bonding on the OH group. Now, if we look at hexane, you see methanol is very poorly soluble in hexane, 1.2 moles per kilogram of solvent. But after that, it becomes very readily in hexane. So ethanol, propanol, all of these are very readily soluble in hexane because now the dispersion forces in the solute can penetrate the dispersion forces in the solvent to form a solute-solvent interaction. So now when we talk about it quantitatively, we're talking about solute, which is undissolved, and solute that is dissolved. And so with the solute, there are 3 different types of solutions. We have unsaturated, means that there's less solute at equilibrium, so you can put more solute in solution. So unsaturated means you haven't reached the maximum amount of solute at a given temperature for that compound. Now saturated means you've put the maximum amount of solute at a given temperature for a compound. And if you added any more, it would cause the compound to crash out. So a supersaturated solution is when you add more solute than the solvent can hold. So it's called what we call crashes out. And this is how some people make rock candy. They heat up water, they dissolve the sugar in the hot water, they make a saturated solution at a higher temperature as they cool it down. Usually when you decrease temperature, solubility decreases. So as you cool it down, the solubility of sugar decreases, and then eventually you reach a temperature at which it becomes supersaturated, and that's where you get the rock crystals, the sugar crystals forming on the string. So how does this look like in a graph? So if we take a saturated solution of sodium acetate, we add a seed crystal. As soon as we add the seed crystal, it causes a kind of like a chain reaction. You get this formation of sodium acetate that precipitates out because now you have a supersaturated solution. So you cause the solute to crash out. And one way you can go from a saturated to supersaturated solution is by changing the temperature of your solution. Now, as I've been saying, temperature does have an effect on solubility. With salts, generally, now this is general, salts are more soluble at higher temperatures. And this is because generally dissolving a salt in solution is endothermic. So usually when you dissolve a salt in solution, it's endothermic. So as you add more heat, it makes it easier for the salt to go into solution. So notice here that dissolving a salt into water is endothermic. Heat is a reactant. So if we increase the heat, we're going to shift to make more product, which is solution. So that's why at higher temperatures, more of the salt dissolves in the solvent. Now with gases though, for solution to be made up of solids or gases, gases is a little bit different. So with gases, solubility decreases with rising temperature. And that's because when you dissolve a gas in water, it's exothermic, meaning it releases heat. And that's because the intermolecular forces of the gas molecules compared to the intermolecular forces of the gas molecules in the solvent, the ones within the gases are weaker than the solute-solvent interactions. So as you add heat, here heat is a reactant, so it's going to shift to make more product. So your gas is going to come out of solution. So if you add enough heat to water, you actually remove the dissolved gases from the solution, which causes the water to boil. So if you want to increase the solubility of a gas, you want to decrease this. You want to do this by decreasing the temperature. Now another thing with gases, we'll get to in a second, but just to show you that most salts increase solubility with increased temperature. So if we look at the solubility curve, you see on the y-axis we have solubility, grams of solute for 100 grams of solution. Temperature we have on the x-axis. So here if we look at KNO3, the line represents saturated solution. So for KNO3, the green line represents saturated solution. So below the green line, in this area, underneath the green line, this is a unsaturated solution. So the area underneath the green line is an unsaturated solution. The area above the green line, this area, we have a supersaturated solution. So by knowing the temperature and the salt, you can determine how much solute is required to get a saturated solution or a supersaturated solution. So for example, here at like 35 degrees Celsius, we said the solubility of potassium nitrate is roughly 25 grams. So if you add more than 25 grams of potassium nitrate into 1 kilogram or 100 grams of water, you're going to form a supersaturated solution. This is how we interpret a solubility chart, curve chart. Now with gases, besides temperature, we can also affect solubility by pressures. Pressure is not very much of an pressure doesn't affect solubility much for solids and liquids because those are mostly incompressible. But for gases, as we increase the pressure, we're going to increase the amount of gases in solution. So as you increase pressure, more gas goes into solution. This is because when you increase pressure, the equation is going to shift in such a way to decide with fewer moles of gas. So when you increase P, the side with fewer moles of gas is the product side, so it shifts to put more gas in solution. And so to calculate the solubility of the gas with the pressure of the gas, we use something called Henry's law constant, or Henry's law, which relates the solubility and pressure of a gas through something called Henry's law constant, which is based on the gas solvent interface. So what gas are you using and what solvent are you using? So solubility of a gas is in moles per liter, pressure of gas is in atmospheres. Now, as you see, as we push down and apply more pressure, we force more molecules of gas into the solution. This also explains why when you open a carbonated beverage, it goes flat over time, because you're reducing the pressure inside the bottle. So more molecules of gas leave, the pressure reduces, less gas is soluble, so more gas comes out of solution. So just a few examples of Henry's law. Now the example 2, I have the answer in the notes section of the PowerPoint, but for example 1, we'll work it out. So here we have dinitrogen monoxide, N2O, commonly known as laughing gas, is mixed with oxygen for use in analgesic uses during dental surgery, so you don't feel the pain. If we have a mixture of N2O and O2, it's 40% N2O by volume and has a total pressure of 1.2 atmospheres. What's the solubility of N2O in water at 25 degrees Celsius? And it gives us the KH of N2O in water at 25 degrees Celsius. So here we have a mixture of gases. We have N2O plus O2. Now we know that N2O is 40% by volume. And we know that the total pressure is 1.2 atmospheres. We want to determine the solubility of N2O. In order to do this, we need to know the KH, which is given to us. It's given to us is for this NO2 water solute solvent system. And we need to know the pressure of the N2O. So we know the total pressure. We need to know the pressure of N2O. So now we have to remember that from Dalton's law of partial pressures, pressure of oxygen plus pressure of N2O equals total pressure. And we know that an N2O is 40% by volume, so we know that 40% of the pressure is going to be N2O. So now we can find the pressure of N2O in atmospheres. 0.48 atmospheres. So now we have the pressure of N2O. We now have the KH. We can calculate the solubility of N2O. The solubility is 0.12 molar. That's the maximum amount of concentration of N2O you could dissolve in this mixture of laughing gas at this temperature and Henry law constant. To give you kind of an idea on number 2, here we want to know how many grams of O2 will dissolve in 2.5 liters of H2O that is in contact with air with the partial pressure of O2 is 0.209 atmospheres. So the way you would approach this is you would, from using the pressure of O2 and its Henry law constant, determine the solubility of the gas, which is in molarity. Once you know the molarity of O2, you know the volume, you can find moles, and then you can find grams. So again, what we did in number 1, we have a mixture of gases, N2O and O2. N2O is 40% by volume. The total pressure is 1.2 atmospheres. So that means the pressure of N2O is going to be 40% of the total pressure. So we can find the pressure of N2O, 0.48, and then we can find the solubility of N2O by multiplying it by the Henry's law constant. So on that note, this is the end of this first lecture on colligative properties. I hope you enjoyed the lecture. If you did, make sure to hit the like button down in the bottom. And until next time, Dr. Armand signing off.